Last time we mentioned about induced matching lemma. And then we use induced matching lemma to prove 6-3 theorem. And left as so previously. The induced matching theorem implies 6-3 theorem that we proved. And I leave as an exercise to show that it also implies Roth theorem on 3-term arithmetic progression. So today let's prove induced matching theorem. That's the first thing we will do. So let's recall the statement. It says that induced matching theorem, if you graph the edge set is the disjoint union. So if I have n vertex sets, and the edge set is a disjoint union of n induced matchings. I don't specify the size of the induced matching. Where Mi is induced matching. Induced matching, recall, it just means that if you look at the vertex sets of this matching and look at the subgraph induced by G, then there are no other edges other than the matching M. So if this is the case, then the graph cannot be too dense. The number of edges in the graph must be little o of n squared, subquadratic. So proof. Before we say the proof, let me briefly just say the idea. We'll see the detail. The idea is after some cleaning the graph, you apply regularity lemma. By regularity lemma, apply regularity lemma on G, you will get this. You do some cleaning. Remember, you get this graph, subgraph of G by cleaning little o of n squared edges. Delete it. So what we're going to prove is suppose otherwise. Yeah. Let's assume our graph G is the union of n induced matchings. And suppose otherwise that we have a counterexample with G having quadratically number of edges. Then we clean little o of n squared edges. This GR still has quadratic number of edges, n squared edges. Now, since the edge sets of G, hence also GR, consists of M induced matchings, then GR has n squared edges. One of the matching, Mi, in GR still is of linear size. Okay, this implies that some matching, induced matching, Mi, has size linear in GR. The graph comes with cluster. This is the regularity partition. We only look at how we look at this matching Mi. You just look at all the parts. Suppose this is the matching, say. It looks something like this. Okay. We further throw away all the clusters where it intersect this vertex set of the matching, which intersect matching negligibly at most little o n vertices. So all these are substantial parts. All right. Since we throw away negligible number of vertices, little o n vertices that intersect Mi at the little o n size for each cluster. So their existent matching edge, after throwing away the clusters that intersect mi negligibly. So let me write it. Consider clusters that has linear size intersection with GR, with mi, this induced matching. Then the thing is, between these two clusters, there's some edge of the matching that survive, and this matching edge is between two clusters that are large and regular, meaning that there are lots of edges between these two in the graph G. Then one of which this edge, the number of such edges that survived, is more than the size of the matching, meaning that there must be some edges between these two dense parts that's not coming from this induced matching, contradicting to the fact that mi is induced. Some edge E in mi survives, which is between, E is between some large and dense and regular pair. Large subsets of implies that there exists a non-mi edge, which is a contradiction. So let's see the details. Suppose we have such a graph G, m vertex, edge set is the union of n induced matchings. Suppose E of G is linear, let's say Cn squared for some C. For some C bigger than 0. Now we're going to take epsilon to be slightly less than C, let's say C over 10, and apply regularity lemma. On G. With a lower bound on the number of parts to be 1 over epsilon, so that the number of parts in this partition is at least m. And since m is 1 over epsilon, the number of edges inside each cluster takes up only epsilon proportion of all pairs, so it's negligible. Then we will get the reduced graph R, which is defined by this parameter. We only put an edge between two clusters if they are epsilon regular and density at least 2 epsilon. Reduced graph. Then this also gives us this subgraph GR of G corresponding to R. We do the cleaning to get this GR corresponding to the reduced R. What's the property of this graph? Well, recall, if this is, say, our reduced graph R, you just look at the corresponding cluster and only keeping edges between the corresponding cluster. You delete all edges inside the cluster. Such subgraph you retain almost all edges of G, meaning the number of edges deleted, number of edges removed equals to EG minus EGR is little o of n squared. So let me write by this choice of parameter, one of the calculation we did before is at most 3 epsilon n square. Okay, this implies that GR has lots of edges. It's at least Cn squared minus the number of edges removed. So at least, still at least, how many edges? Epsilon is at least, C is 10 epsilon. So you have 5 epsilon n squared edges. Now, sorry. So the number of edges deleted is less than half. I shouldn't write like this. Wait a second. Yes, that's fine. I just want to write this is bigger than Cn squared over 2. Okay, so you retain half of the edges at least. This implies what? Now, as I said, G consists of edge set consists of n matchings. So is GR. So that means one of the matching MI still has at least Cn over 2 edges survived. I pigeonhole exist an induced matching M with at least C EGR over n induced matchings in total, right? So at least Cn over 2 edges in GR. And so here's a picture. So suppose right? Suppose this picture looks like this. This is our cluster. Yeah, so this is the induced matching. Immediately, we should notice that the vertex set of the matching is at least the size of the matching, right? Well, if you have one edge, you have at least 2 endpoints. 10 edge, 20 endpoints. So the size is at least Cn over 2, implies that the vertex sets is at least Cn of this matching. Good. Now, we define, look at this intersection. We only cared about each cluster, the part intersecting the matching M, right? This is the part intersecting the matching M. Some parts intersect very few. We throw away this part. So let's do that. To do that, we define, you have this VI, Vj, right? This is the cluster. We're going to define Ui to be each cluster intersecting the vertex set of M. Okay, for each I in R, for each cluster. You define how the parts of each cluster intersecting the induced matching M. Now you throw away the negligible part. So what I mean is you only keep let U to be the union of Uj, Ui, union of Ui, where Ui is at least epsilon fraction of Vi. okay, I in R, which is the pink part here. You only keep those that are large, takes up epsilon proportion. You throw away this. Now this is my U. Good. And now I just look at M restricted on this set U. First thing to notice that at least one matching edge survive. So we have all vertices of the matching, which is the union of all UI. From UI to U, in this process, we throw away those UI that are small. These take up at most epsilon proportion of the small one, and the union of all UI is N. So the total number of vertices we throw away from here to here in this process is at most epsilon N. We discard at most epsilon N vertices. Okay. This means what? We know a lower bound on the number of vertices of M. This implies U is at least Vm minus epsilon N. But Vm is at least Cn size. Epsilon is 1/10 times C. So this is at least 9/10 times Cn. Okay. Nine over 10 times Cn, that means one of the matching edge in M must live in U with M, both endpoints in U, right? Because if this is your M, how to remove vertices so that all matching edges of M disappear? You have to remove one endpoint from each edge. You have to remove M number of edges. Maybe I don't need to write this. What I want to say is the number of edges, number of vertices we discard is this many, which is less than the size of the matching, Cn over 2, which is less than the size of the matching. This implies that some edge of M survives in U. Okay. So let's say this is our edge, survived in U. Let's say XY. Some edge XY of M survives in U. So what is this pink part? This is UJ, right? This is UI. So let's look at UI, UJ. First of all, they live in VI, VJ. And each UI, UJ, by definition, they are part of U. That means it takes up epsilon proportion. So this is large. Then, by definition of a regular pair, that means the density between UI, UJ is very close to the density of VI, VJ. This edge XY lives in between some dense and regular pair, VI, VJ, say. Then since ui by our choice is bigger than vi, uj is bigger than vj, we get that the density of ui uj is at least the density of vi vj minus epsilon. But remember how we define reduced graph? We define reduced graph with density at least 2 epsilon. So the density between vi vj is at least 2 epsilon. Minus epsilon, we get at least epsilon. This implies what? This implies what? Oops. This is regular means there are lots of edges in between. More than the possible edges in M. So you have edges in M. Maybe it looks like this. But I have many other edges. So there is such an edge with M points in U, which is the part of vertex set of the induced matching, but this edge is not the matching edge. Implies that the number of edges in G between ui uj is at least epsilon times, it's a density times ui uj, right? Ui uj, which is n squared. Let me be a little bit brief here. Ui uj is linear size. So this is n squared. N squared, when n sufficiently large, this is much, much bigger than n, which is bigger than the size of the matching. This means there existent num m edge on Vm, because Vm contains the set U, which contains this ui uj, a contradiction. Contradicting to M being an induced matching. Okay. Any question? Okay. If there's no question, this is all I want to talk about for induced matching theorem. Next, I want to talk about by now I will say a classical applications of removal lemma. Another application. C63 incidence graph. Point line incidence graph. So let me first explain what does it mean incidence definition. So given a points lines arrangement, planar one, on the plane. So for example, you have 3 lines. Maybe let me add one more. How do I draw? Maybe like this. Let's say we have 4 lines and the points are here, 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 here. Okay, and maybe here. 1 second. These are the points P1, P2, P3, P4, P5. You have some points. Oops, maybe 2. Maybe like this, yeah. P1, P2, P3, P4, P5. Okay. An incidence is basically a pair, PL, points and lines, such that the point lies on the line. So this is an incidence of P3 and L2. This is an incidence of P5 and L4, so on and so forth. Okay, here's the incidence of P1 and L2. And the number of incidents is the number of such pairs. And here we cared about counting the number of incidents of a point line arrangement. So here on the example, the number of lines, number of points, number of incidences. We have 4 lines. We have 5 points. What's the number of incidents? Let's count. P1, L2, so 1. P2 lies on L1 and L2, so 2 incidents for P2. P3 lies in L2 and L3, so also 2 incidents. So you can see 1 for P1, 2 for P2, 2 for P3, 2 for P4, this 2 line, 2 for P5, also this line. So everything is 2, 2, 2, 2. This one is 1. We have 9 incidences. We can record this into all this information in the bipartite graph. This is called the incidence graph. For a set of points and a set of lines, which is a bipartite graph where you have points and lines as vertices. You have L1, L2, L3, L4. Okay. Then you put an edge when the point lies on that line. So P1 lies in L1. You have an edge, P1 to L2, sorry. P2 in L1 and L2, so it's like this. P3 is in 2 and 3, 2 and 3. P4 is in 1 and 3. 1 and 3. P5 is in 3 and 4. 3 and 4. So this is the incidence graph. So this is a bipartite graph on partite sets P and L, and P adjacent to L in the graph if and only if you have incidence. Then notice the number of edges in this incidence graph is exactly the number of incidences, right? Whenever you have an incidence, for example, this P3 lies in L2, you have an edge. The number of edges in this graph is the number of point line incidences. So now we're going to focus on the special family of bipartite graphs that are point line incidence graphs, that are incidence graphs of points and lines in the plane. There's a famous theorem by Semerity-Trotter. One quick remark I want to say is for any point line for any incidence graph, of points and lines on the plane, it must be C4 free. Okay, what does it mean C4? You have points and you have lines. C4 would have mean you have 2 points lying at the intersection of 2 lines, which is impossible. If you have 2 lines, their intersection point at most 1 point. So you don't have C4. Does it make sense? Usually for C4 graphs, you have an M vertex C4 free graph. We know the number of edges is of order of magnitude n to the 3 halves. We have this construction from projected plane, realizing this n to the 3 halves upper bound. So the famous Semerity-Trotter theorem is saying that from this C4 free, although it's C4 free, we have in general big O of n to the 3 half upper bound. But since incidence graph of points and lines in the plane are very special, it's very geometric, coming from this geometric arrangements, we can get much better bounds for such graph. We can get big O of n to the 4/3 number of edges. For any points and lines arrangement, with P equal to L equals to N, you have N points and N lines, then the number of incidences is big O of N to the 4/3. In other words, for any incidence graphs of points and lines in the plane, if it's G, then the number of edges is n to the 4/3. We will not prove this now. I want to talk about a strengthening of an extension of this is assuming for point line incidence graph, we don't have C6 in there. Now consider now C6 free point line incidence graph. Recall, normally what do we have? If you have C6 free graph, the number of edges maximum is n to the 4/3. You could have a matching lower bound of n to the 4/3, C6 free. The next result we're going to see is this n to the 4/3 lower bound cannot be realized. It's impossible for point line incidence graph in the plane. We will get, for C6 free point line incidence graphs, we will get the upper bound of little o of n to the 4/3. It's different from the general case. This is the theorem. For any m by m vertex point line, this just means we have m points and n lines, okay? Incidence graph G. Then C6 free will imply that the number of edges will drop from big O of n to the 4/3 to little o. Okay. So before proving this, let's first see what C6 free means. Well, you have these points and lines. C6, for example, looks like this. P1, L1, P2, L2, P3, L3. This is a C6. Let's look how it looks like in this point line arrangement. You have P1, there's an edge between P1 and L1. That means P1 as a point in the arrangement lies on the line L1. So you have L1, and you have P1 somewhere here, okay? What do you know? You also know that P1, there's incidence between P1 and L3. So P1 is also lying on L3. So L3, L1 intersect at P1. We are done with P1. Let's look at P3. P3 is a point on L3. So P3 is somewhere here. P3 is also a point on L2. So it's the intersection point of L1 and L2, L3 and L2. Now, at the end, we look at P2. P2 is actually an intersection point of L1 and L2, right? So this is P2. So C6 corresponds to, in G, corresponds to this triangle arrangement. You have 3 lines and 3 points in our point set are the intersection points, pairwise intersection point of these 3 lines. Good. So once again, this theorem is saying if you have points and lines on the plane, this arrangement, if we forbid this kind of triangle configuration in this arrangement, then the number of incidences cannot be n to the 4/3. I forgot to say this bound is tight. There are arrangements where you realize n to the 4/3. So C63 says you cannot realize the maximum anymore. In fact, there is a conjecture, I think still open. People believe that C63 incidence graph n vertex actually should be n to the 4/3 minus c number of edges. Getting a polynomial in n improvement will be very interesting. So this is open. We only improve from big O to little o. What's the idea? Let me first say the idea. This basically, what's happening is a lot of graphs, the idea is that lots of graphs, meaning graphs from obtained from geometric setting, from geometric settings, like this point line incidence graph, many such graphs do not have a uniform edge distribution, meaning that they have their edges clustered or non-uniform distributed. What does it mean? Why is it helpful? Well, in the case of bipartite graph, since the edges are not uniformly distributed, then somehow we can zoom into some parts that has density much higher than the average density of the graph. Then oftentimes on this much denser part, we can obtain better results than generic graphs. Okay. So then that means we can zoom into some exceptionally dense parts. This in our proof is done. In this proof is done by Matuszak's partitioning lemma, cutting lemma. Then we will zoom into this part, and in this case, we then apply removal lemma. Triangle removal lemma to finish the proof. So let's see the details. Let me first give some preliminary. Let's recall this Matuszak's cutting. Let me introduce this theorem. Lemma Matuszak's cutting. It says the following: for any point sets P on the plane R2, set of, let's say, m points, and any parameter R between 2 and n. I should say there exists an absolute constant C. So let me not write this. Let me try to write this. Exists R between 2 and n. Let me start over. For any set of endpoints, for any parameter between 2 and n, then we can find a partitioning, a cutting of the points at P. P is partitioned into regions, parts, D1, D2, into T parts, where T is between R and R over 2, and each part is almost of the same size. Each part, DI, has size at least n over R and most 2n over R. Each part is of size up to a constant factor 2, same size, which implies the number of parts of T is linear in R. Okay. What's important is, so here's the incidence graph point of view. You have points and lines, right? We can cut it P into D1, DI, DT into T parts, such that each part roughly the same size, and no matter which line you take, it only has incidences, it only cross points in at most square root R regions. What does it mean? If you now look at, in terms of graphs, the incidence graph, for any points L, it only passes through points. In other words, in the incidence graph, this point L as a line, it only has neighbors each vertex L in L has neighbors in this many parts. Remember, the number of parts is linear in R, but the parts you have neighbor is lower order term in terms of the number of parts. This is important. That means the edges are clustered, right? Every vertex does not send neighbors uniformly across all parts. They are clustered. So this is the first theorem we will use to zoom into this dense part with larger density. Okay. So let me illustrate a little bit. What do I mean? This exceptionally dense. In our proof, I'll illustrate it here. In the proof, suppose the number of edges is not little o of n to the 4/3. It's n to the, it's not little o, so that means it's big omega. It's linear in n to the 4/3. Then we will use this Matuszek's cutting, the first thing, to to zoom into some parts DI and some subpart L, some subset of lines, subset such that DI is roughly n to the 1/3 size, and L prime is roughly n to the 2/3 size. And the number of edges, incidence in between, is n to the 2/3 incidences. We can use this Matsushita's cutting to zoom into these parts. Why I say this is exceptionally dense? This is exceptionally dense. Think about it. Our original graph has n by n vertex. Number of edges is n to the 4/3. If you do a pure random subset, pure random n to the 1/3 and n to the 2/3 subsets. Okay, here I take n to the 1/3 like DI. Here I take n to the 2/3 here like L prime. What's the expecting number of edges in between? Expecting number of edges is you have n to the 4/3 edges total. The endpoint lies here, an edge, the endpoint lies here. The probability is n to the 1/3 divided by n. The right endpoint lies here. The probability is n to the 2/3 divided by n. What's this number? This is n, cancel. So you have this divided by that. That is n to the 1/3. Once again, if you do things purely randomly inside this graph, n by n vertex graph of number of edges n to the 4/3, you will only get an expectation n to the 1/3 edges. But since this graph it's a point line incidence graph, the edges are clustered, which is captured by this cutting lemma. We managed to zoom into a n to the 1/3, n to the 2/3 parts, where the number of edges is n to the 2/3, much, much larger than the random one. And then we win, okay? Later on, we're going to define an auxiliary graph, which consists of edge disjoint triangles, and to apply triangle removal lemma. I will continue this proof next time. Today, I have to finish the course a little bit early. Any questions so far? So I haven't give you the proof yet. I just mentioned the idea, and this lemma. Okay. Next time, we're going to use this lemma and triangle removal lemma to prove this theorem. Okay. This explanation is to say, through this, for geometric graphs, we can sometimes, like in this case, Matsushita's cutting lemma, we can find much, much denser parts than in generic graphs where we do things randomly. All right, if there's no question, we will continue on Thursday, same time as today. See you then.